Hey folks, welcome to another episode of Advent of Code in F Sharp. Day 23 already. There we go. My track record is getting spottier and spottier, but I'm trying to keep up, so let's see what day 23 has in store for us. Unstable diffusion. We enter a large crater and go through a lot of story. I already read this during my morning coffee, so I'm kind of skipping over the story part. So we're planting seedlings, or the elves are planting seedlings, and we scan the grove, which is our puzzle input, and we note the position of the elves. We have a 2D grid again. Elves are those hashtags, and dots are empty ground. And this is just a limited view because everywhere else it's empty ground, so we have an infinite grid again. North is up, we have orthogonal directions. Yep. Elves follow a time-consuming process, and we would like to simulate it for a number of rounds. And each round consists of 2 halves. During the first half, each elf considers the 8 positions, so we're also looking diagonally. If no other elves are in one of those 8 positions, the elf does not do anything. So no neighbors means we twiddle our thumbs. Otherwise, we look in each of the 4 cardinal directions in a specific order and propose moving if one step in the first valid direction according to some rules. So it's a riff on Game of Life. Yeah, it's a riff on the Game of Life kind of thing. After each elf has had a chance to propose a move, not move yet, the second half of the round can begin. Each elf moves simultaneously if they were the only elf to propose moving to the position. So there's a couple of interesting twists here. Cool. If 2 or more elves propose moving to the same position, none of them move. And the preference, those 4 rules, the preference changes, or they move round robin every round. And then we have a smaller example to get started with. Cool. First things first, infinite space or infinite grids means we need a data structure that can handle this, or we have to grow it incrementally. But let's take a data structure that can have an infinite grid. For example, a map or a lookup table, which maps. Or no, not even a map. We don't care about the world, we care about the locations of the elves. So I think just a set of the elf coordinates would be enough, is my assumption. So let's provide a type. So our grid is a set of locations, which is an elf location. And location is nothing more than a 2D a tuple of a row and column. I was thinking about the problem from yesterday. What was day 22 again? Don't remember, but it was also something 2D, and I kept tripping up between rows and columns and X and Y coordinates, so I'm not even going to mention X and Y today. I'm going to work with rows and columns. So first is the row number, second is the column number. I think 3 slashes should give me intelligence. Yeah, there we go. And our grid is a set of locations that only contains the locations of the elves. If it's not in the set, then it's an empty space. And that's infinite for you. Let's parse our input, or let's parse one of the examples first. We have a small-ish example and a large-ish example, and then we have our massive input. Let's work on the small example first. We just need the lines, yeah. We don't need to split on anything special today. So we have our lines. Yep. What are we going to do? We just need to know the row number, the column number, and whether or not there's an elf in there. So let's grab every row, let's grab every index of a row. So this should provide us with the row numbers. Yes. And then we can loop over that. So for the row number and the row itself in this thing, we can yield something. Let's yield whatever, the row, just so it compiles and we can see whether or not we're okay. We're okay. So what do we do for every row? We just iterate again. So for every column number, cell in row, which is indexed again, we should yield something else. Let's yield the cell. And we're nesting comprehension, so there has to be a, there we go. Row is a string, yes, row is a string. So let's keep it sequence instead of a list, because a string is a sequence of characters implicitly. Okay, we seem to be enumerating all the things, and we know the row number and the column number. We can filter if cell equals an elf, then we yield, let's get rid of the arrows, let's do yield everywhere. So then we yield row number, column number, and otherwise we don't yield anything because it's an empty thing. So I think this is our list of elf locations. 1, 2, 3, 4, 5. Does that make sense? 3, 4, 5. Yeah, and you should have 2 next to each other on the first row. Or the second row with the index 1. Yeah, looks correct. And if we just set that, we should have our parsed grid. That returns the grid. Yeah, there we go. Let's now parse a small example again. Should work, should result in a grid. So we have locations of all the elves, which is all the state we are going to need. No, that's all the state of the world we're going to need, but we also need to have the which or the order of the rules we need to apply, right? Yeah, so we need the cardinal directions. Let's also encode that into a type. So that's northeast, southwest. Either of those. There we go. Let's floop that into the REPL. There we go. Okay, back to the drawing board. What's the next step? We have to do a round, and a round was 2 halves. One is considering positions, the other is doing the motions. Do we need to know which elf is trying to move? Because now we just have a set of locations. Yeah, we kind of need to know which. We kind of need to know which elf is trying to act, right? We could represent an elf by its location. Yeah, that would work. If we know the original location and the new desired location, that's enough of an identifier. So what are we going to do? We're going to write a function that plays around, or that does a round. Do a round given a grid, and it should return a new grid, so we can do this indefinitely. And a round consists of 2 phases, or halves. First, we consider 8 positions adjacent to themselves. Okay, so do we need the neighbors thing again? That's something we've done 1,000 times before, so let's go and make it quick. Row is the first thing, so -1 is the row above, and column to the left. Above, directly above, and above to the right. And we need to do this on the same row as well. We don't need ourselves in there, or our current location. And we need to look below as well. So these are all the neighbors. Oh god, what am I doing? Yeah, that threw me off, but that's basically what we want, right? Yeah, looks correct. So those are the neighbors, or the offsets, and if we then map those offsets and apply them to our current X and Y, we have all the neighbor locations. The neighbor locations. There we go. Neighboring locations, that sounds even better. That's something we are going to need, or we could use to figure out the neighbors. And we also need to look at a certain subset of neighbors, right? North, south, northeast. So we need to be able to look at 3 neighbors in a given cardinal direction. I'm just gonna write a separate function for that. Does it make sense to first look at all the neighbors, all 8? Yeah, we kind of need it for this first part of the first half, right? Then they just nop, they stay. And otherwise we have to do this rules thing given try north, try south, try west, try east kind of thing, and this rotates every round. So we have to look in the 3 northward or southward, westward, eastward. Let's write a function for that. Let neighboring neighbors to, how do you say that? Neighbors to my north location, to the north of my location. Yeah, let's call it neighbors to. And that was called what? A direction. And we need a location again. And again, it gives us 3 neighbor locations, or a location list. That's good enough. So let's pattern match on direction. Let's keep it simple here. So if it's north, we need to look up in 3. We need to take a look at the 3 cells to our north. So north is 1 row higher, it's -1. And again, with an offset of 1 on the column. In our east, what do we want to look at if we look east? Everything where the Y has incremented by 1, right? Above us, right to the right of us, and below us. South will be this, I guess. So everything drops 1 row, and west will be -1 here. Does this look somewhat symmetrical and according to our expectations? North, yes. South, yes. East, and the column is incremented by 1, yeah. And the rows differ, and here it's decremented by 1 on a column and all the 3 rows. Yeah, so these are the offsets again. Let's apply them. These should be our neighbor locations. So we now can look at all 8 neighbors, and we can look at 3 neighbors given a cardinal direction. That's all we need for phase 1 of, or half 1 of a round. So let's... What's the order here? North, south, west, east? Let's also encode the list of directions. So there's an order to it. North, south, west, east. And let's... Are we going to do an infinite loop? Yes, we're going to do an infinite, infinite lists. Let's not do it recursively like that. Let's do sec init infinite so we can keep repeating this thing to eternity. There are more performant ways by just doing index and modulo calculations, but this is a cooler approach, right? And we flat map it, or we flatten the list. There we go. Will this bite us? This will definitely bite us. Do I already regret this decision because I have seen this cause performance problems in the previous day? It's too cool not to try. So we have our directions, and we just take the next one off every time we do a round. So let's grab this do round function we're trying to write, and next to the grid let's also provide the directions. And that's infinite, so we can always destructure it in given direction and the rest, because that will never be empty. And it's a sequence, not a list, so this will not work. So let's do direction equals sequence, the head of this infinite sequence. That's the current direction that has preference. We should take 4 actually. Let's take the 4 first directions. Those are the priorities for the direction this round. And then we just nibble off 1, and that will end up at the end. So this will work. So those are the 4 priorities we need to take a look at. First, we need to take a look at, do I have any neighbors? So we are looping over the elves, which is our grid actually. Should call this elves, right? Let's call this elves. Parse a grid into elves. Yeah, sure, that all still makes sense given these new terms. So for every elf, no, let's drop into the set.map returns a set, right? Yeah, we don't want that. We actually want to have duplicates if there are any. Can you iterate over a set? Does this work? Yeah, cool. So a set is a sequence thing. So let's drop this into the list world, sure. And we are trying to look at the neighbors. Those are the locations, those are not the neighbors. But that's okay, yeah. So that's... What am I doing next? those are not the next locations. So these are the neighboring locations. And let's count those. So if the list is empty, that's what we're trying to do here, then the elf stays the same. Otherwise, the elf does something. And it is empty, not empty. Cool. So we're doing something for every elf. We're looking for, do I have neighbors? No, then I don't do anything. Otherwise, I need to do something, and that's what we still have to spec out here. What do we have to do? We have to apply those rules. We know the 4 rules to apply because of those directions we have just fed in. And then we take a look at the neighbors, or we count the number of neighbors in that direction. Okay, this is following along nicely. So, else. I'm taking a look at, do we always need to move to the next direction in order? The first direction the elves considered, but what is considered? Do they actually, if no elf has like taken a, if no elf has a neighbor, does that count as having considered a direction? Yeah, if I look at this, yeah, sure. Okay, that was a small detour, sorry. It's a small detour because the problem is getting less clear in my head and I'm deferring any critical thought. But let's dive into the critical thinking here. So we have 4 directions. We know we have a neighbor somewhere, so we should end up with... We know we have a neighbor somewhere. We don't know where. It could be that they have 8 neighbors, right? And then nothing happens. Is that true? So say we have an elf with 8 neighbors. If no other elves are in one of those 8 positions, that is not true, so we continue. The elf proposes moving north, south. Yeah, it looks like there's this state where you potentially could have 8 neighbors and none of the rules apply, so how do you know what to do in that case? Probably it never happens, probably you just stay in place. Yeah, let's assume that. Anywho, we need to go over those 4 rules. And the first rule that applies is the one in that's the direction we have to take. Yeah, let's assume we always one of these rules applies, and it'll crash if it doesn't, and then we know we have to think a bit more on that. So we have to find the first of those directions in this priorities thing where we have no neighbors, right? Yes. So from these priorities, let's find the first. Find returns the first element for which the function returns true. So that's what we need. Where neighbors to my north, east, southwest, given my current location. And where that is empty. So that's the direction I'm going to move in. And then I'm going to move this elf in the direction. We don't have a move yet, that's correct. Let's write a move quickly. So that's a location and a direction And it should return a new location. And that's just pattern matching on the direction, sure. We've done this before 10 times already, so x decreases by 1 if we look north. It increases by 1 if we look south, or if we move south to the east, we increase y, and to the west, we decrease y. I've seen people use complex numbers to represent 2D operations. That's also something cool if you are interested into marginally cool mathematics that are useful for an additive code puzzle. But I'm not going to go there today. I am just trying to have my elves move a bit. So that's the direction, and we move this elf. So these are the proposed moves. And let's also return the original elf. So proposed moves. So this is every elf proclaiming, I'm trying to go to my right. Or I'm trying to stay in the same place. These kinds of things. So we have this. I think that's part 1. Or this first half of a round. And then we should do the move if we are the only ones trying to go to that location, and otherwise we cancel each other out. And then we rotate the directions, or those priorities we call them, and then we're done. Easy peasy, lemon squeezy. So second half, each elf moves to their proposed destination tile if they were the only elf to propose moving. If 2 or more elves propose moving, none of those elves move. So if we group our proposed moves by destination, all the ones that just are the only ones trying to go there, they do move. And if we have collisions, they have to stay in their place. I'm foreseeing a bug where my elves multiply because of what I'm trying to do here. So if we have elf multiplication, it will be on line 39 and below. Anyway, so proposed moves, let's take small steps here, is proposed moves group by, let's keep it in the list world, group by the destination, which is the second, it's the second element in the tuple. So we are grouped by destination. And I'm going to do something dirty here. I'm going to give this function an alias, so it's a bit more clear, a bit more readable what we're trying to do here. It's a mini abstract data type. Shenanigans. So yeah, we have our moves grouped by destination. And now for every group with one. Yeah, so let's map our grouping. Or even collect our grouping. No, let's first map it. So a grouping, what is a grouping again? Is that the actual tuple? Yeah, cool. So that is if we're mapping, we have our destination with our proposed moves. And let's return depending on the length of the collisions, we can do something. So if our proposals if we are the only one trying to go there, or if there's only one elf trying to go to dest, it's dest. And otherwise, it's not dest. Otherwise, we have a collision and we just return the original locations. So that is proposals, list, map, start. So if we have a destination that is second, we have a start that is first. And if we put this in a list, our return types are all the same in our if-else statement, and this now returns if I grab this in a variable to show you, this is now a list of a list. It's a location list. That's not what I want. I want a set. So I'm going to flatten this first, and you can flatten a list of a list when you're mapping by just doing the same, but then collecting. Now this is a single list, and I don't care about lists, I care about sets. So this is our next phase. I think that is it, except the rotating directions thing. So we can do the rotate in here, or we can do the rotate in a calling function. I'm gonna do the rotate in here. So this is our next elves, or our moved elves. That's this thing, and we just return moved elves, and the order of rules we need to do. So that's a direction sequence and a new set of elves. And it's a type, so we need to have type syntax. For a tuple, no comma, but asterisks. So there we go, and then we return what? We return directions minus the one we just used. And it's a tuple. There we go. This is a beefy, a beefy method or a beefy function. It's 27 lines. That's a lot for an F# function. But there's a clear, if we wanted to extract some functions or stuff like that, that would work. I'm not gonna bother. I'm not even gonna test it. I'm gonna verify by eye. So let's grab the smaller example. Do I have a parse somewhere? Yeah, in here we have a parse. Yep. And it's elves, not grid. We changed our mind midway. So this is the original set of elves. And we had our directions or infinite list somewhere. Let's grab that one as well. A bit closer to what we're trying to do here. Those are our directions. And let's try to do a round. Given the directions and given our current set of elves. And let's see what we get out of that. That's the new directions and the new elves deconstructed. Oh, key not found exception. Oh, we're already hitting the one edge case I thought would not happen. Interesting. But we know immediately what the problem is. We're doing one single sequence.find in those priorities. So we have the case where we have neighbors somewhere and we're trying to look at one of the 4 cardinal directions, like where is it free, and here it's saying it's not free nowhere. You have neighbors in all 4 cardinal directions, sorry. So let's do a try find. And if it's nothing, we stay where we are. Wait. Oh yeah. We need to move first. So let's I'm taking too big of a step. I'm sorry here. I'm trying to keep it all in one pipe. So I'm doing an option bind, an option.map, an option.map, and then I want to map my direction, one of those 4, if we have one. And I'm trying to move here. And so now the move has happened within the option. And if I now do default value, I can say, okay, but if we don't have one of those 4, so if this was none, then stay where you are, stay at E. So that was a very badly explained way of lifting something into the option monad by doing a map. Yeah, types line up, it compiles. I'm pretty sure this works. And I'm pretty sure we got rid of the key not found exception during our sequence.find. We did. Cool. So these are the new locations. Are we going to verify by eye, or are we going to write a printing function? We're not going to print. Smaller example. So we have original elves at 1213, 22, 4243. Yes, and then we move to. That does not look correct. Our elves have not moved. Something went wrong here. Our elves have not moved. Interesting. Probably there's a bug in here, right? I was not expecting it to. I should have thought more when we had that key not found exception. I don't think that maybe that was necessary. I think that maybe we have a bug in here. Let's verify. Which elf do we want to have moved? This one, we want to go to the north, right? So the elf at 1, 2, the first one, we want to have that one go north. Do our directions start with north? Yes. Is north the initial rule? Yes. Everything lines up, so there's a bug in our function somewhere. Cool. Let's figure out if we have neighbors to our north. Given 1, 2. What does this thing take again? A location, direction, and a list of locations. A list of locations? Excuse me? Huh? Oh no, it returns a list of locations, I'm sorry. Confused by the type signature. This kind of sounds correct, right? That this is the north neighbors we want, so that's not a problem. Our move might be a problem. I'm not seeing the problem, but let's let's try to move north. 1, 2, moving north should be 0, 2. That all is working. What is happening? Okay, we're off to debugging. Let's print out our proposed moves, right? What was it? The round has 2 halves. What do we have here? Yeah, let's see if we calculate the first half correctly. So our first elf is not moving. Nothing is moving. Everyone is staying at ease, soldier. So our bug is in the first half already. That is somewhat surprising, actually. No, it's not surprising. Let's see if we have neighbors that, or if we have elves that have no neighbors. Do we have any of those in the example? No, we all have neighbors, so that should never happen. This should never happen. Never. Let's see. Let's clear the REPL. Yeah, that's never happening, so cool. Debugging without the debugger. That's my preferred style. No, it's not my preferred style. Somehow I never got into the habit of debugging F# scripts. So I just print a lot. I'm going to print everything because I'm not sure where the bug is actually. So priorities, and then we try to find direction. So a direction where the neighbors in that direction are non-existent. So we have an empty list of neighbors in the cardinal direction. Yeah, and then we try to apply the move. So let's print out something in here. We're moving to direction, and the elf is trying to move in that direction. Yeah, let's see what this gives us. Were we expecting 5 prints of priorities? Oh yeah, because every elf is taking those rules in that order. Yeah. We're never moving. We're never hitting this. So we never find a direction with neighbors. Okay, interesting. So probably a problem here. Neighbors of this elf in to this cardinal direction. Where did my IDE go? There is my IDE again. So debugging some more. Neighbors of this elf to this direction are neighbors. So let's print it out. Either. Let's extract this. Neighbors. So we're extracting a variable to not open our debugger. That's okay. There we go. What's the bug? I'm curious. If I have screwed up columns and rows, no, that won't even be the problem, right? Neighbors of 1, 2. Oh, yeah, I've been here before. Those are not the neighbors, those are the neighbor locations. That is a pretty obvious bug in hindsight. Whoops. Yeah, okay, so those are not the neighbors, those are the neighbor locations. Wow, and it's because I did not write tests, but also because I did not name my functions well. Neighbor locations to the north. Do I have the same problem for my 8? No, there we did the right thing. There we did rename it correctly. So filter those neighbors where our elves contains this location. I don't know what I was trying to do here. Actually, should this not work? If you have a function with one argument, should you not be able to... Ah, no, it's this pipe operator. Okay, didn't say anything. So, and this is the same problem. Yeah, we do have the same problem here. I'm not awake. So, elves set contains. So these are the neighboring locations. We're only keeping the ones where an elf exists, and if there's no elf, then this happens. Yeah, and here the same kind of makes me think that we don't need neighboring locations and neighbor locations too, but we need to write the neighbor functions as well. Oh well, I think we're done now, so I'm not too bothered about it. I'm not here to write the cleanest of code. I'm just trying to write some F# and get my star fruits. That's better, right? I think that's better. That looks correct. Oh yeah. So after 45 minutes and some nasty bugs, because I write big functions, don't test, and have bad naming skills, I think we're there. So we can do a single round. Can we do more than one round? So this is... Wait. Yeah, okay, so this is the first state, and then there's a second state. Let's do that one as well, right? And the process ends when no elf needs to move. Let's just write the entire loop now. Because the process ends when nothing changes, when no changes are proposed, and we only have 1, 2, 3, 4, 5 elves. In our input, we will have a bit more. Let's see how many. No, let's not. Let's not worry about that. I'm trying to explain that. What is the halting condition for this infinitely looping thing? No changes were proposed, or the elves stay at the same location. So, fixed point again. We've seen this before, I think, in one of the previous days. Let's write a fixed point function that just tries to move, and if the result is exactly the same as our input, we know that we have reached some kind of stable state. So let's write a fixed point. And we need our elves. And we need the directions. And that's it, right? So we need to do round stuff. Next direction, next elves. And if the next elves set is exactly the same as our input set, then we are done, and we can just return one of those. And otherwise, we need to go one more round, so it's recursive. We go with the next set of elves, and yeah, we need to go with the next set of elves, so that's a little do round. Oh, fix, sorry. Given the new elves and the new directions, because we went crazy and built an infinite list for that. That's the fixed point function, so that will keep looping until nothing changes. And my hypothesis is that we're done. So let's grab our actual input parsing. Let's drop it below all our functions. And let's calculate our fixed point. That went over quickly, but it's a small example, so that could make sense. So we have an elf at 102, that is correct. 1-4, yes. 2-0, yes. 3-4, yes. 5-3 something, 5-2. Yeah, correct. So wheat. Now we could run the same thing on our larger example, and that should reach a fixed point after 10 rounds, but we don't care about the number of rounds, we care about the end state, right? So let's try to run it on the example. So no more small. Let's print out every elf we have and verify by ear or by eye. By ear, what am I saying? Okay, -2. it's getting a bit more complicated. -2, is that our smallest coordinate? That does not sound correct, right? 4. Our top row has a 4. 0, 1, 2, 3, 4. Oh no. Oh no, sorry, we're not calculating the fixed point. We're calculating 10 rounds. I think this might be part 2 already. Yeah, this might be part 2 already, so let's pretend we didn't do this already, and let's just run 10. Let's just run 10 rounds. So I'm gonna keep this fixed thing here, because we might need it, right? And let's write a new function, repeat, that does not keep looping, but that stops after a number. And it's the same principle, so it is if the number is 0 or halting condition, or base case for the recursion, then we are done. Otherwise we do a round. I flip directions and elves in arguments and output, and it's a tuple output, so I'm not sure if I like that, but let's not worry about that. So then we just repeat. And we decrease number, of course, or we'll never finish. Did I just see that correctly? No, I did not see anything. So we can repeat. Is it 1 or 0? If you say repeat 10, we might. Let's. No. I don't know. Actually, I don't know what I have to type here, so let's figure it out by visual inspection. Repeat 10 times. I'm not sure. Why is it staying at -2, 4? Nothing changed. Let's print our number of iterations. I was not expecting to have another bug in there. So yeah, we're doing something for 10 times. That's for sure. The top row should have not have 4, right? The top row should have 1, 2, 3, 4, 5, 6. So not something is not going according to plan. I guess there's only one thing to do here, and that is take smaller steps and do this larger example round by round. Will it make sense? Would it make sense to start printing out the grid for visual feedback instead of just coordinates? I think so. We have 7 more minutes until we hit the hour mark. Yesterday, I spent, I think, half an hour on printing my data structure out again, but I'm gonna go for it. So let's write a print. Let's write a print. So elves is a set. We need to know the width and the height of our grid. So we grab our rows. So these are rows and these are columns. And then we can grab the max and the min. I don't know what I'm doing here. There we go. So that's the minimum row, the maximum row. This is something I have to do a lot. And I don't know if there's a cleaner or a more concise way to get like the minimum and the maximum out of a sequence in like a less than 2 steps, 3 steps. I don't know. If you have a solution for that problem, I would be interesting. Or I would be even interested. I don't know if I'm interesting, but I would be very interested in that that little tidbit of information. So that's the minimum call, that's the maximum call. And then for row in, row min, row max, for column in, column min, column max, yield row column, just to verify. And let's not type the return value, so we can play around with it first. How do we print? We print our elves, of course. Let's print our initial elves. Is it not called print? Print grid, sorry. Print grid given these elves, go. So we go from 0, 0 to 0, 6, and then we go to the next line. 0, 0 should be... What is the initial example we get? Yeah, 0, 0 to 1, 2, 3, 4, 5, 6, yes. And then 1, 2, 3, 4, 5, 6 as well. Yeah, that is correct. So if this coordinate is in our set of elves, it is a hashtag thing, and otherwise it's a dot. So if elves contains row column, then we have an elf, otherwise we have an empty space. And that should print out our small window into the infinite grid where all our elves live. And we'll print out sorry, what did it say? Type character is not... Oh yeah, it should be a string. We're printing strings here. And let's print new lines at the end of a row. So that is... Can I do that like this? It appears to compile, so let's give it a try. We're printing a new line at the end of every row, and we're printing out every column of every row. And it's returning me a list of unit. I don't care. Don't return. Yeah, and now we can type it unit again. So that makes more sense. It's a very obvious side effect here. And we are printing stuff, and that appears to be somewhat correct-ish. That appears to be totally correct, right? I think so. And I did not even mess up my X and Y coordinates. Win. That is a win. So let's repeat. Oh, will it be enough by 1? I'm going to be pretty disappointed with myself that I did not think about that. But let's print grid of the result. So we have taken one step. We might have taken one step. And that looks nothing like... Oh, sorry. That was the initial state. Does that look something like what we expect? I'm looking at like the spaces in between to quickly verify. It kind of looks correct, right? Oh no, it looks correct. End of round 2 then. Kinda looks correct as well, right? What was I doing wrong? Yeah, looks the same. We have 3 more to verify. And hopefully we see a problem. Two between, 3 between, yes. 3 between, yes. And then we have 2 between, yes. Oh god, there won't be a problem, will there? I probably did something wrong. Yeah, this looks correct. Let's see here. Yes, yes. Yes. Yeah, sure. Correct. Correct. Oh dear. I'm not seeing any problems here. No. So we have one more. Oh, well, I was like thrown off by the 4 in the location for the first one. Could it be that 4 is correct, but that somehow they move around a bit? Could that be? Could that be? That would be a devious example to provide into today's puzzle. That would be heinous, devious. Oh, no, there's not a problem. Why is this happening? There's like an empty row, right? Yeah, no. Did we spot something here? What's going on at round 5? Why am I seeing an empty line? Interesting. I'm not convinced that that's supposed to happen, so let's take a quick look here. It looks correct, but for some reason there's this empty white line that I'm not expecting. Yeah, let's print out those coordinates again. That's a set, not a list. Okay, so we have 1 on the top row, yes. And then we skip a row, yes. And there's 1, 2, 3, yeah. And then there is 1 on, yeah. So that all appears to be correct. So let's drop to the 1 to last. So that should be 7, 7. And then we go back 1, 2, 3. So that should be 7, 4, 8, 4. And then 3, 2, 8, 1. That my coordinates look okay. Why is it printing a new line? Why is it doing this? So we are at 7 and 8, right? Yeah, we are at 7 and 8. Huh? Did I have the same problem with my 4th generation grid? No, that looks squeaky clean. Huh? What's the bug here? Where are you coming from? I'm not sure that this is the problem, but I'm gonna... put some brackets around it, around my comprehension. I'm not even sure why. I have this like gut feeling. And this gut feeling is very helpful. That is not the direction I want this to go in. Oh yeah, it has to be outside of the inner loop or the inner comprehension. So maybe this, maybe this. I love it when my explanation or when my calling my shots results in yelling, maybe this. It means I'm clueless. It's not a good place to be at. So no, that's not a bug. Should I worry? I should not worry. I think we might even be messing about with stuff we don't need to mess about with. Let's see that 10 result again. That appears so correct. I cannot even. That was correct. It's just that me seeing a -2, 4 in there, given our starting layout, confused me. But that's actually not a problem. That's perfectly fine. So let's call this okay enough, and let's see what they want us to do to calculate our input or our answer. So after 10 rounds, which is where we are right now, given the example, yeah, after 10 rounds, that they like to make sure that they are making good progress towards covering enough ground. To do this, count the number of empty ground tiles contained by the smallest rectangle that contains every elf. It's literally what we had to do for printing. So we have to calculate the bounding box containing all the elves. And we don't have to go with non-orthogonally aimed rectangles. Thank you for that. So we calculate the bounding box. That is easy. And we count the number of empty ground tiles. We know the number of elves. We know the... What's oppervlakte in English? Surface. Whoa. We know the surface because we know the height and the width. Yeah, we can figure out how many empty ground tiles we have easily. So let's calculate the bounding box, which is exactly what we did for our printing. That's actually a good name to calculate the min-max. The question I had a second ago. I want to know the bounding box given a set of coordinates. So let's write a function. And it's a x min. Alright, it's this whole thing, right? So let's grab this whole thing. And let's return min row. Will a tuple of tuples be clear enough? I'm gonna confuse myself, so let's just return a structured type here, a record type. I'm gonna keep it in row language, not in XY, because that will confuse me. And let's do a range thing that has a minimum and a maximum. So we're freewheeling a bit here. This is totally not necessary. But hey, it's the 23rd of December. I have a holiday. I'm having fun. So let's freewheel. Let's write a bounding box function. And now we can return our box with our row, having a minimum and a maximum. And our column having a minimum and a maximum as well. And there we go. What's the problem? Semicolon. What's the problem? Points. So this calculates a bounding box given a sequence of points. Let's put that signature in there explicitly. And let's type this in our location. That's not a location, that's a single. So yeah, this is fine enough. Let's stop boilerplating. Or hypothetical boilerplating. We don't even know whether this works. So this is the box. Let's extract the function, or let's use the function we extracted. in our printing as well, because why not? Oh, look at this. We could even have a type or have a function on bounding box to give me the range, but let's keep that for us a next step. Keep my steps small, keep them somewhat small. We can clean this up if I feel like it in a second even. There we go. So I'm hoping that my printing still works. Yeah, it seems to do something. Now we can also do bounding box. So we have a bounding box and we can calculate the number of elves in that box. Which is 22 in the example. Could that be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12? Yeah, could be 22. So surface is the distance between the surface of my bounding box, of course. So that should be max is always bigger than min, right? Doesn't matter. We need to distances. The distance between 2 points. What is the distance between 2 points? I would like to see 10 in this case, right? Not 6. So max minus min. Is that always the distance if the 2 points are ordered in increasing length or in increasing value? I'm trying to figure out, do I need absolute value? But after an hour, after more than an hour, my brain is fried enough to not have an answer for that. So let's just not worry about that. So I think this is fine. This is fine. What could possibly go wrong? So this is one dimension, the row length times the column length. Those are always the, next to the stupid bugs, these kind of wild assumptions are always the things that cost you hours while programming. So we should have surface minus number elves being solution to part 1, 88. Sorry? Why was my surface 110? What is the definition of empty? Is it just like the surface of this rectangle? We don't need to deduct the number of elves. I'm going to assume that we just needed to calculate the surface, so the 110. So this can all go out the window. Let's verify that. So that's a 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, let's drop to an editor that can show me column widths and line number of lines. So we have 11 times 13. 11 times 12. What is that? $120 and 12 is 120, 32. It's getting too late. 120 plus 12, 132. Yeah. Okay, minus the 22 elves should be 110. Yeah. So my area calculation seems to be off. It should be 11 times 12. 11. Why am I saying it's 10? Someone's at the door. I'm gonna have to cut the stream. Sorry about that. Someone at the door. They're gone now. Christmas period. All my neighbors are receiving packets, and I'm the go-to house, apparently. But if I am correct, we were figuring out what the problem was with our number of free spots in the bounded rectangle thing. And I think that my surface calculation is incorrect. Because if I look at the surface, it's saying 110, and that's not what we're expecting. We're expecting 132. And if I take a look at what we're doing, we're taking the distance between max and min, which is, let's print out our bounding box again. Its first coordinate is -2, or the minimum row, and the maximum row is 8. And I'm doing the difference, which is 10. That's not what we want. We want, there's 11 spots between -2 and 8, right? I think so. So I think if we do this, so that turns into 11, yeah. And for our columns as well, so that's -2 to 9, that is one more, so that should be 12. So I'm guessing this should be 132. Yes, it is. And now we can grab our free elves, or number of elves, sorry. Result should be 22, and now we have our results. Minus number of elves, 110. There we go. This is for the example. That seems to work. So now let's run it on our input and hope we don't burn up our CPU. That was a bit slower. Let's print our grid. Stuff has happened. Our bounding box is bigger. It's still a nice rectangle. Our surface is a lot bigger. Our elves are a lot. There's a lot more elves in there, and we have a number. Let us hope. Let us hope that is the correct number for part 1. Great success, first try. Awesome. Let's continue to part 2. It's a bit on the slow side now for only 10 iterations. I'm guessing we're going to have to calculate the fixed point now. It seems we're on the right track. Finish simulating the process and figure out where the elves need to go. How many rounds did you save them? Oh, we just need to know which round. We don't need to know the end state. Yeah, so we need to figure out 20 rounds here until we reach the fixed point. So we can get rid of this bounding box, counting number of elf things. We don't need to do repeat, but we need to grab the fixed point. And instead of only returning the end state, we need to count the number of iterations. So let's get rid of this repeat. We don't need that either. Let's start at 0 and have a counter in our fix. So if we have reached the fixed point, let's return the iteration number and the elves, and otherwise let's return +1, of course. Let's increase our iteration counter and let's print out our iteration just for fun. So that's a digit iteration. There we go. I guess that's part 2. We don't actually need to print. We don't even need the result. We just need the iteration. And for our example, the full example, I guess. Yeah. For the full example, we should like it to return 20. 19. Almost. 20. There we go. So if we do this for our input now. Yikes, what happened? There we go. There we go, off to the races. Oh no, it's going slower and slower and slower. Assuming this won't reach an end state fast enough. Where can we improve? Where is our time going? Where are our precious CPU cycles disappearing to? Our representation is a set that's logarithmic axis. Is it? F sharp data types set. What are the properties of our set? We are checking for contains a lot. So that's a logarithmic operation. We're mapping over the set, so that would be linear probably. Is a map a linear operation? It has no map. At least we map or we iterate over every element to get the next generation of elves. So yeah, that's logarithmic and linear. Can we do much better? We can do much better. We could do constant and constant time for one of the two lookups at least. Can we memoize? Is there a cycle in there? That's maybe something we can quickly detect, whether or not we have cycles. So our fixed point will not only keep track of the iteration and the current state, but also like a list of visited states. So let's provide next to the one an empty set that represents the history or all the visited states. If we calculate a new value, how do we calculate a new value? I mean, we do it here, but can we keep it tail recursive? Does it matter if this stays tail recursive? Yeah, let's keep it simple for now. So next is this. If visited contains next, then let's crash so we have an error message when we have a cycle. Otherwise, fix it or is this correct? No. So we recursively call the thing. That's not gonna work. That's not gonna work. Sorry for this. Let's get back. Let's keep it tail recursive. I was right all along, and let's add do round. That's what I'm looking for. Oh Jesus. I'm sorry for this. I was confusing myself. So Control Z. Let's go back to something that worked. There we go. This is where we do the next thing. Okay, so this is where we were. Let's say we pipe in visited, and if new elves is in the visited set, then we want to print out something. Let's see if there's cycles in there. Otherwise, loop over, do the next iteration of fixed point where we add this calculation or this Should we also keep track of the direction we're at? Probably. So, sorry. Sequence of direction does not support. Okay, cool. So let's keep in the first. Our infinite list. Oh, that's a big one. That's a big performance headache right there. Let's get rid of that infinite list next if we don't have any cycles. So we update the visited list so we can detect cycles quickly. There we go. Should all still compile, should all still work. Let's see if it works and whether or not we have a cycle. If we don't have a cycle in the first whatever's 100, we know enough. Yeah, there's no cycles. So probably the thing that is eating up precious CPU cycles is line 149 to 151. This was a neat trick, but it's a useless trick and it hits some of my CPU cycles. So let's get rid of it. Let's write a function. And instead of piping through all the future directions we should take a look at, let's keep a simple index. Or maybe even a list of 4 and we just keep shuffling that. Yeah, why did I make it infinite? Oh dear. So instead of making it infinite, let's have a list. There we go. It's going to be faster if we don't even do this, because taking an element from the front of the list, that's up constant time, but prepending it to the end of the list, that's linear time. And we don't want to waste any cycles, so let's write a function. What is it, modulo 4? So we made things more complex than they had to be. Sorry, let's define n being 0, so that should get us north. Yes, n being 3 should be east. And n being 4 should give us north again. Yes, so this can go up. All the way up. Let's put it around the direction type, sure. And now we can do direction for round and keep in the round number instead of the sequence of directions. Where are we calling our functions? Here, fix set empty directions. Directions is not okay. Let's get rid of that and let's use our round number. So let's do iteration -1. Okay. Do round takes a iteration or round number. And to get the directions. Oh, we don't need. Oh, God. Yeah, okay. We're getting there. So this priorities thing, directions, no. No, let's keep it. It's gonna be a bit better. So from round number to round number +4, +3, sorry. Map that to direction for round. Let's map that. I was saying let's map that and I don't write map, so confused. So those are 4 priorities and everything stays the same. Here we don't provide directions, so that can go 2. And here, fixed point should not take directions either, that can go. And here we don't need to include directions either. And the thing that do round returns can be cleaner as well. It should just be elves now. So we're getting the next directions out of there. Yeah, all makes sense. All still makes sense. This is not the most performant way to grab 4 priorities, but it will work, and it will be better than the infinite list, so let's try that first. And this just returns the new elves. And then we don't need to keep track of this. Let's also get rid of the cycle detection because it was useless. There was a non-cycle detection if statement in there. There we go. Cleaning up a bit. After ourselves. There we go. There we go, there we go. Cleaning up. No more need of an empty set to keep track of state. Fixed point returns iteration end state. That's still correct. Let's see if this goes a bit faster. A bit, but not much. Let's see if it's still correct for our example before we run too much. So the example should end up with 20, right? Yeah, still 20, so that works. Let's see. It's faster, but not the fastest. But now at least it's increasing linearly. And it's not slowing down. I'm guessing we're still gonna have to wait a couple of minutes. How big would it be? Would it be in the millions, billions? If so, there would be a pattern to the outputs. Let's say we don't have... Oh, it ended. I was thinking of like seeing how fast the dimensions grow. But no, it's below 1,000 iterations. And if we get rid of crazy infinite list things that don't work that well in F# or that consume a bit more precious resources, yeah, I'm happy. So I was thinking we could maybe take a look at the widths and the heights and see how they grow and find some kind of mathematical sequence in there and then deduct. That would never work because we need to know when we reach a fixed point. So forget I said anything. It was just a bit heavy on the CPU today. Lovely little puzzle. I enjoyed part 23, or day 23 at least. Let's quickly go over what we did as an executive summary and then call it a day. So we had to simulate elves moving a bit around until they all were settled in and had no immediate neighbors. So we had a 2D grid, or we just kept track of the elves in a set, so we didn't need to model the empty states explicitly. It was an infinite grid as well, so it does not make sense to use an array or something. It had to be a map or a set. So we went for that. Then I tried to be very clever and used an infinite sequence of directions, and apparently that was not the most performant way, so we dropped back to array indexing and modulo. Parsing was pretty basic, as long as I don't mix up X, Y, and row column. That's something I do for 11 years in a row. As long as I've been programming, I can't keep apart those things. But today was fine. This is the typical neighbor calculation we've seen 1,000 times before in previous Advent of Codes. There was a little twist that we only had to look at 3 of the 8 neighbors, depending on what direction the rule was pointing. Applying a move is also pretty basic. Then do round is where things got interesting, because we had to move in 2 halves of the round. First we decide where we would like to go, and then we figure out whether we can go. So that was interesting. We did a lot of option things, and I think if I rip out the option, it would still work. I'm gonna try that. because I think that might have been overkill. So if we just do this, and then do the move. So do the same thing, but without the option. So now we assume that every rule, or at least one rule, triggers for every elf in every generation of those 1,000 rounds. I'm guessing this still works. So let's see. Oh no, there are cases. Interesting. So yeah, that assumption does hold. We have elves that sometimes have no rule that applies to them. So that was a bit ambiguous in the problem description, or at least I interpreted ambiguously. That's a difficult word. I interpreted it ambiguously. But yeah, our do round thing just takes the current situation and the current round number, so we can get the correct directions for the rules. We do our 2 halves with some option monad magic. And then we figure out in the second half whether or not the elf moves or stays put by grouping and counting the number of identical destinations. And then for part 1, we just did 10 iterations with a repeat function. For part 2, we tried to find a fixed point, or we did find a fixed point. So that's just looping until the current iteration has the same result as previous iteration. I am having trouble speaking here. Whoa. But if that's the case, then we have reached a so-called fixed point and we can stop, and that's the iteration we were interested in. I found my bounding box abstraction to calculate min-max in 2 dimensions, so happy about that. Not happy about these 6 lines, but yeah, that's how we do it. Printing was useful for visual debugging, and having a bit of patience until we reach 900-ish iterations gave us our 2 star fruits for the day. A lovely puzzle. I'm hoping we go out with a bang with 2 more interesting puzzles. And me, myself, I have to catch up a bit. There's a lot of puzzles where I started but then got stuck with some kind of a weird thing and decided not to upload any videos for that. I'll come back with a summary once I muster up the courage to resume those puzzles. So yeah, that's all I've got for today. Thank you for watching Advent of Code in F#, and I hope to see you tomorrow for more goodness. Bye-bye.